Started on this. I did some stuff over the last few days, not being able to do Mardi Gras because someone stuck a knife in my back. And I found out, I have found a way to make it much easier for y'all to compile Verilog on your own computers without having to download the giant, massive Vivedo, and that to do it on a Mac or a PC. And I'm going to be writing up instructions for that. And I think that, and I'll also do some videos on how to use a test bench, because one of the other problems you have with the lab and only having the limited time is you can't practice on the board if you don't have the board, but you can practice with a test bench if you know how to use it right. So I'm going to be working really hard on getting that ready, and y'all also gave me some good advice about putting together some sample programs that you can look at to like get ideas of how to make things work. So that's kind of my project. And I'm really lucky because one of the classes that I'm about to start, it's a condensed class, is a graduate education class on preparing multimedia resources, like as an educator, how as an educator to prepare multimedia resources. And so I'm hoping I can adapt all of the projects to be preparing stuff for y'all. So hoping that all works out. All right, so now we are going to be drawing a circuit according to this Verilog module. And I started to do one like this in a session, a month ago, but it was going to take too long, and so we didn't get to it. But it is important to know how to do it, because this is a kind of question that he tends to ask. So when you look at it, you see you've got a for loop. You've got this vectored signal that's named Q. That's kind of a big hint, Q. So that's probably going to be a flip-flop. These are almost always going to be flip-flops. They're almost, I remember what it was. I wanted to show you what to do if the input to the clock was not a clock on a flip-flop. Remind me to do that after I finish this problem. So it's a callback to question 1. So this is our clue that we're going to have some flip-flops. And you almost always use D flip-flops because they're the ones that make the most sense. You also see an if statement. An if statement is almost always going to be a multiplexer. It doesn't have to be, but it makes sense for it to be a multiplexer because that's what a multiplexer is. And so just to remind ourselves of how a multiplexer works, here's our multiplexer. If this is a 2-to-1 multiplexer, we have a single input that's a 0 or a 1, and we have a single output. And based on what S is, that tells us what our output is. So this is X over here. So this multiplexer is the same thing as saying if S equals 0, then X equals A, else, and the else would be the same as saying if S equals 1, then X equals B. And so what this multiplexer does is the output of the multiplexer depends on both this select input up here, which tells you which of these 2 ports to choose, and then what the actual value is what's going into that port. So let me give y'all another example and see if you can figure this one out before we go on to the code. Yes?
Do you have to put the else if S equals 1, or can you just do else?
You can just do else. You absolutely, that was not code. That was pseudocode. If it was real code, I would have had parentheses and double equal signs.
Okay.
Yeah. Okay, so here's my multiplexer, and I'm going to say A equals 0, B equals 1, and I want you to tell me what is the value of this multiplexer what is the value if S1, S0 is 1, 0? So S1 is 1, S0 is 0. What value is F in that case?
0.
And where did that 0 come from?
Corresponds to the input where you have 2. You have A and B. If A is 0 and B is 1, that is A 0 and 1 is 0.
Yep. So 1, 0 is the binary number 2. So my input for this multiplexer is 2. And so that means since the input is 2, my answer is going to be whatever is coming in at the 2 port. What's coming at the 2 port is A and B. So I need the AND of A and B. I need the AND of 0 and 1, and that would be 0. Okay, what if S1, S0 equals 0, 0? Then what is the value of my multiplexer then? I think I heard it. 1. Because S1, S0 equals 0, 0 corresponds to 0. What's coming into the 0? 1. And so that's going to be what F is.
We have to read the S's in binary.
Yes, you do. Yes.
Would we be asked to write this in Verilog?
Possibly.
Okay, I have no idea.
But we're not there yet.
I got
I'm trying to make sure you understand how multiplexers work, and then I'm going to show you how we're going to use it in some Verilog. And then to write this in Verilog would be more of a lab thing than an exam thing.
Okay.
But it is possible, and it would not be that hard. Actually, I'll show you as soon as we're done with this how you would write this very thing in Verilog. Yeah.
Can you run it down one more time? Why S1 and S0? If S1 and S0 equals 1, 0, how is F equals 0? Well, before that one.
Okay, so if I have S1, S0, there are 4 possibilities. 0, 0, 0, 1, 1, 0, and 1, 1. So these are the binary numbers 0, 1, 2, and 3. When I look at a multiplexer, if it's a 2 to 1 multiplexer, I'm going to have the numbers 0, 1, 2, 3 right here. And then depending on what value S0 and S1 is, that's going to be what my output is. So for this first one where I had S1, S0 equals 1, 0, that's binary for 2. So I care what's coming into the 2 input. I don't care about anything else. It wouldn't be Digital Logic 2 SI without that. And so what's coming into the 2 input is the AND of A and B. So I have to know what A and B are. A and B are 0 and 1. The AND of 0 and 1 is 0.
Okay. Got it.
You got it now? Okay. All right. So let's just do the other 2 possibilities. What if S1, S0 is 1, 1? Then what would F equal?
0.
It would equal 0 because 1, 1 is 3. And so it'd be 0 because that's what's going into 3. And if S1, S0 is 0, 1, F would equal
0.
It would equal 0 because it's A. Well, what is A? A is 0. Okay, so the question is, how would you do this in Verilog? You do it with a case statement. So I put together, actually I put this in parentheses of case, and then in parentheses, a case statement, what it does is it says you can have, it's like an if-else, but you can have any number of values you want. And so, and I'm saying my case statement is based on S1, S0 stuck together as a binary number. So this is saying take S1 and S0 and put them together as a binary number. Now I know that there are 4 possibilities here, and that would be the binary number, and this means what I just wrote means 2 bits and binary. So it's two digits in binary, 0, 0. That's my first possibility. My second possibility is 0, 1. My third possibility is 1, 0. And my fourth possibility is 1, 1. Because I know that there's nothing left out, I don't have to put the default. I covered all the possibilities. If I had some don't cares in there, then I would have a default, but I don't. And so that's all of them. And then end case. And then for each one of these, I would then say F equals 1, F equals A, F equals A and B, F equals 0. And that would be it. So that's how you would write that in Verilog. Yes?
Can you also do that for 1 digit?
Yeah, so for a single digit, so if I had this multiplexer, and we're going to see this in the code that we're about to do. You would probably do that if S. If S is a shortcut for if S equals 1, you can certainly put equals 1 if you want to, but you can more likely to see just if S. Since we only have a single statement, we don't need a begin and an end. I would say F equals X, semicolon, else F equals Y, semicolon. And that would be the multiplexer for that. You look skeptical.
Because there's no 0, 1 values like that. Like it just says if S, like there's no like if S equals, you know.
Well, she said that S, you could put it as if
I said
S
you could.
equals 1.
Oh,
I said it's a shortcut for that.
okay, never mind.
Yep, that's okay. No, I'm glad you asked, because if you missed it, someone else probably did too. So, yeah, so it's just a shortcut for writing if S equals 1. Because what everything is a 1 or a 0. So what does it mean to say if S? If S. S is either 0 or 1. This is either in true is 1 and false is 0. So if S is 1, that equals true. And if S is 0, that equals false. So it means the same thing. All right, so now that we are experts on multiplexers, and we became experts on flip-flops and problem 1, let's now draw this out. So I'm going to give you some clues or some shortcuts. If you see something like this on the test and you're kind of overwhelmed and you're not sure what to do, first of all, you can be pretty sure if you see a for statement, you're going to have a series of flip-flops. It's going to be some sort of register. It doesn't matter if you know that's what it is or not, but that's probably what you're going to have. So you can draw those. And you can get an idea as to how many you have by looking at your numbers in here. If this says reg n-1 to 0, n-1, well, what's n? N is given up here. It's a parameter. It equals 3. That's just a constant, so it's just 3. So register 2 to 0. So that tells us we're going to have 2, 1, 0 are going to be how many flip-flops we have. Oftentimes, not always, but oftentimes with these flip-flops, we are going to have a multiplexer associated with them. And when you see an if statement inside the for loop, you probably are going to have a multiplexer. I'm not going to guarantee that you will, but you probably will. And so I'm going to go ahead and draw it, because maybe at this point on the test, I don't know what I'm doing, but I know, hey, Rebecca told me that this was a good way to start, so I'm just going to do this. And I'm going to have the output of the multiplexer go into the input of each of the flip-flops. Those are supposed to be little trapezoids. And these are supposed to be D flip-flops.
How do you know they're D flip-flops?
Because those are the only ones that are useful for you to use. Because with a D flip-flop, the value is just whatever you put in it. And it just holds on to the value for a minute, which is why we're using it. It's a little bit of memory. And if we were to use a T flip-flop, we probably could, but we'd just be making the problem a whole lot harder. So when you have the choice, you would choose to use
so
D.
we have the choice for, okay.
Yep. Okay. So another thing, so at this point, if you still don't know what to do, you can say, well, I'm probably going to have a clock, so I'll put a clock in here. All right, and there, you've done some stuff. So now you can say, all right, I'm making some progress. All right, now let's take a look at the for loop and see what's actually happening. So in the for loop, it's going to tell you what the inputs are for your flip-flops. And it's going to tell you if you need to use the multiplexer or not. So this says for j equals 0, j less than n minus 1. So j equals 0, so that'll be the first one. And then the next time around, j will equal 1. That's still less than n plus 1. The next time around, j will equal 2, which is not less than n minus 1, because n minus 1 is 2, and 2 is not less than 2. So I only have to do j equals 0 and j equals 1. Okay, so j equals 0. If y, so that means if y equals 1, this is telling me, all right, it's an if statement, it's a multiplexer, and it's saying if y equals 1. Now, that means y is the input into the multiplexer. So what is the thing that's inside this if is going to be the select for the multiplexer. And then since we're at y equals 1, it's telling us what to put into the 1 port of the multiplexer. So we're at j equals 0. It says it says q of 0 becomes equal to the naught of q of 1. So what does it become equal to? The naught of q of 1. The naught of q of 1, which is right here, goes into the 1 input of q0. So we're at, it's saying q0, so that's this multiplexer. q0 is this multiplexer. If y equals 1, that's this 1 right here. What does that need to equal? It needs to equal the naught of q1. Else, q0 equals the OR of x and q of 1. Okay, so if that was the input into the one input of the multiplexer, what is the else going to be the input into? The 0. So we need to say that what's going into the 0 of the multiplexer has to be the OR of x and q of 1. So I'll have an OR right here. And I've got some other variable here, x. Just draw it right here, x. And the OR of x and q1 goes into the 0 input of that multiplexer. So now if you look at q of 0, it's fully defined now. We don't know where its output might be going, but we know its input is, if y is 0, it equals the OR of x and q1, and if y is 1, it equals the not of q1. Okay, I'm going to give y'all a couple minutes to see if you can figure out what to do for j equals 1. We just did j equals 0. Now what would you do for j equals 1? So you're going to go through these same two steps, but now you're defining the inputs for the multiplexer for q1. So see if you can figure that out. It's not hard, and it's not a trick. Yes?
Is it okay if you could explain how we know it's only for 0 and not also for 1 and 0?
Because I'm doing them one at a time, because that's the way I'm presenting it. It is the same for 0 and for 1.
I'm sorry.
Yeah. No, it's okay. No, it was a good question. It's because I was going through the for loop once, and now we're going through the for loop again.
I didn't mean to spoil that.
Oh, no, I don't think you did. Because if they already got it, they had already gotten it, and if they haven't gotten it, you didn't give it away.
Okay.
Yeah.
I thought when y equals 1,
Uh-huh.
so why do we have to do like the not of x to find the 0 of the multiplexer?
It says if y equals 1, but y could equal 0. So we have to come up with both alternatives. If y equals 1, you have this, and if y equals 0, you have this.
But it's not gonna tell us if it is or isn't. Like we just have to make it both.
You have to draw it to accommodate anything, because in part B, they're going to say, okay, well, let's do some examples where we're going to tell you what x and y are. But x and y, those are switches on the board. You can switch them to be whatever you want them to be.
Okay.
Yeah, but we have to draw it to account for any scenario. Okay, so as the spoiler told us,
I know.
1 is going to be the same as 0 because it's the for loop for 1 and 0, so it's going to do exactly the same thing, getting the values from 2. So we're going to have the not of q2 is going to go into 1, and then the OR of x and q2 goes into 0. All right, so now we're done with the for loop, and then it tells us q of n minus 1. N is a constant. N was 3, so this is just saying q of 2 equals a. So I have another variable, and hey, there's no if. It's just saying it just plain equals a. Well, I told you we might not have a multiplexer, so this one doesn't have a multiplexer because there's no if. It's saying it just equals a. So A goes straight in to Q2. Then we are going to assign B to be the output of Q0. So there's B. And then we end our module. And now we're going to have mic drop. Now we're going to use this circuit that we just drew, and say, all right, well, what if we have some particular values? What will our next values be? So it's saying that Q equals 1, 0, 1. What that means is, so 1, 0, 1, this is Q0, this is Q1, this is Q2. So when we start, those are our values. We have Q2, Q1, Q0. Our starting values are 1, 0, 1. And for simplicity, we're saying A, X, and Y just happen to not be changing. A each time is going to be 0, and X and Y are going to be 1. And actually, these were the former values, and we're starting here. And we need to know the next values, and we need to know the value for B. Okay, Q2 is easy. What did Q2 equal? This is looking at our circuit. This is Q2. Q2 is going to be A. So it'll be 0. Q1, well, Q1, it depends if Y is 1 or Y is 0. Y, we are told Y is 1. So if Y is 1, then Q1 equals the naught of Q2. So what would that be? You have to look at it from the time before. So it'll be 0. And what will Q0 be? It'll be 0. No. It'll be 1. It's going to be the naught of Q1. And then B is the output of Q0, which is 1. Okay, on the next clock cycle, Q2 is going to be 0. What will Q1 be? 1. What will Q0 be? 1. And B? It's going to be 1. Okay, and I just say 3 clock cycles? Next, yeah. Okay, so then what do we get? What's the next one going to be? Q2 would be 0. Q1? Q0? 0. And B? B, let's see, where are we assigning it? It's assigned, we're assigning it after we've come out of the always block, so yes, you're right. Yep. Yes.
We said if there's a case statement, so like if else inside of a for loop, it's mostly always going to be the multiplexer for the if statements. What if it's not in a for loop, would it still be a multiplexer? Or no?
If statements are going to be multiplexers.
Most of it, like even if it's not in a for loop?
Yeah. I mean, that's just the easiest way to do them. You don't have to, but it's just like, it sure is a lot easier than trying to figure out how to do an if statement with and or gates, which you could do, but I don't recommend it. Okay?
Can I ask a question?
Sure.
For the code above that we were given, we have assign B equals Q0. So since it's the blocking assignment instead of the non-blocking assignment, would the B be connected to the multiplexer?
Is the B inside the always block?
Oh, no.
No.
Okay.
Got it? but excellent question. Okay, other questions?
And here it doesn't matter that the clock's positive edge, or the flip-flop's a positive edge triggered or whatever.
Nah, it doesn't matter. It's just happening once per clock cycle. All right. I'm going to, any questions from Zoom? Okay, I want to look at one quick example of a flip-flop Okay, so I have a sequential circuit here, and I'm going to say that I'll just call this Q1 and Q0, and I'm going to say that Q1 and Q0 both start at 0, and I want to know what the values are at each after each edge of the clock. Okay, so here we're starting at 0, 0. When the clock next changes, what is Q1 going to be?
1.
Q1 is going to be 1. Why did you say that correctly?
Because when the toggle is on and we reach our positive clock edge, then it just acts as if it's a normal toggle. We just toggle that.
That's right. So I have my input into the T flip-flop is a 1. And 1 means it's going to toggle. That means every clock cycle it's going to toggle. That means I know I got this. I got half this question right. If it's a 10-point question, I've got 5 points. This is 0, 1, 0, 1, 0, 1. It has to toggle every time. The hard part is what Q0 does, and that's going to depend on X as well. I'm just going to say X is, I'll have X has the values 1, 0, 1, 1, 0, and those are just given. Those are just given. Okay, so at this point, the input into the clock for the D flip-flop is the output of Q1. This is a positive edge triggered flip-flop. A positive edge triggered flip-flop, if this is my clock cycle, a positive edge triggered flip-flop changes only once every clock cycle when the clock goes from 0 to 1. So only when the clock goes from 0 to 1 does it change. The rest of the time, it just stays with whatever value it has. So when we started, Q1 was 0. Q1 is the input into the clock for Q0. So Q0, which is right here, is not going to do anything until its clock input goes from 0 to 1. Well, look what happened at step 1 here. So this was step 0. Step 1, the clock went from 0 to 1. So that means it's going to do its D flip-flop thing, and the D flip-flop thing is to become whatever your input is. Its input is X, and X here is 1. Okay, on this next step, on step 3, did the clock go from 0 to 1? No, so it's not going to do anything. It's just going to stay where it is. On the next step, did the clock go from 0 to 1? Yeah, so it's going to do the D flip-flop thing, which is to, its output will be what its input is. Its input is 1, so it ended up not changing. From 1 to 0, didn't go from 0 to 1, so there was no change. And then from 0 to 1, that is a positive edge, so its output will become its input and it becomes 0. Okay, any questions on that? Okay, all right. I didn't mean to stop the share, I meant to stop the recording.